Yeah, can you show us like number 29?
29, this one right here?
Yeah.
Okay, so like that. So the instructions are to, in the following exercises, use the ratio test to determine the radius of convergence of each series. All right?
Before
So-
you start, Mr. Ingle.
Is that the instruction? I thought the instructions were different.
But before you continue, last week you gave 3 examples. You said that n factorial is going to go faster than a constant to exponential.
Yeah.
Is there a third one?
And polynomials.
Polynomials.
Those are the slowest of the 3.
Okay. And then, man, what was that one? Oh yeah, if it was x to the x.
That
Is it
goes
still gonna be
faster.
slower than? Is it still slower than?
Yeah, so like, yeah, that's interesting. Which is find x to the x and, x factorial. Maybe
X to the x,
n
yeah.
to the n
Yeah.
and n factorial. Which of these is going to get bigger faster?
Yeah.
Yeah. I think. Well, notice this is a product of
Sums.
n things, n
Yeah.
factors, right? 1 through n. This is also a product of n things.
Yeah, but
Because this is n times n times n, or n
Right.
times.
Okay.
Yeah,
So in both these cases, you have the same number of factors. But
the n to the n is greater factors. Yeah.
because all of them are n.
Yeah.
Whereas this one, only one of them is n, all the rest of them are smaller than n.
Less than n. Yeah.
So I think it's, yeah, I think in that from that point of view, it's clear to me that this is going to increase faster than that.
So it's
Now, whether it's decidedly faster,
What's that mean?
like, can I say that n factorial is much smaller? I mean, sometimes something might be bigger, but it's not like
Significantly.
yeah, it's not significantly faster. Not enough in terms of like a ratio to make a difference.
and but at this we're looking at like in-run behavior, right? We start asking
Yeah.
these questions.
Yeah.
So what does it do at like 100?
Well, like for
It's
example,
easy to
like,
do that far, but-
for example, like 2 to the n and 3 to the n. Certainly, this is bigger than that.
Yeah.
But can I say it's decidedly bigger?
No.
And I haven't really defined this in a specific way.
Mhm.
We're just kind of like saying it's in an intuitive way, But yeah, so like, this right here, I'm not sure, if that's justified. So it's like, it's more than just bigger. It's like a lot bigger, whatever that means.
Infinitely bigger.
So
Yeah.
what would you call n to the n? Like we have factorials, polynomials, and exponential.
I don't know. I
It's
guess we can make up our own word for that. I don't know if there even is a name for it. If there is, I haven't heard it. So, yeah, but yeah, you're right. That would increase faster than in factorial. And if I had to guess, I think it's probably decidedly faster.
Decided.
Yeah. Mhm.
For this one, I thought the instructions was like find the interval of convergence,
Mhm. Yeah.
right?
Mhm. Mhm.
Okay.
Yeah. Use the ratio test to find the interval of convergence.
Have you already written the test?
Yeah. Oh yeah, I've written it.
I've written thing too.
Yeah, so like in this case, so the ratio test says we need to consider the limit as n gets huge of the absolute value a sub n plus 1 and a sub n, and see what you get. That is to say the absolute value of, I'll go ahead and do what I saw you guys doing. You just went ahead and simplified the fraction in the first step. So like n plus 1 factorial cubed over 3 times n plus 1 factorial times x to the n plus 1 divided by that, which is the same thing as multiplication by,
Reciprocal.
yeah, we have a, think of this x to the n as being in the numerator. So this would be like 1 over. That's a mess.
Yep.
But the advice I gave you yesterday was to kind of group things together that kind of go together, right?
They look like they go together.
Like we got like 4 factorials floating around, but I think these two kind of go together because they're both cubed. These two go together because they both have that 3 on the inside. These guys go together because they both have an x.
Right.
So I think in my next line I would go ahead and say limit, it goes to infinity, of n plus 1 factorial cubed over n factorial cubed, 3n factorial over, I'll go ahead and do this some algebra here. How about 3n plus 3? Okay?
Factorial.
Yeah. And then I have x to the n plus 1, x to the n. And we'll look at each of these 3 cases. And also I noticed that everything in there is positive anyway.
Yeah. So you don't need
So I can drop the absolute value.
Excuse me.
In this first case, we've done a few of these before, and I can see how some things are going to cancel. But before I think about that, I have to worry about that 3. Where each of the top and the bottom are cubed. The way I'm going to deal with it is I'm going to just recall some pre-calculus and know that if you have a cube divided by a cube, it's the same thing as just the fraction cubed. So far, so good.
Could you? I'm sorry.
Uh-huh.
Never mind.
Yeah. In the second fraction, I can see that I have 2 factorials,
Right.
but one of them is bigger than the other.
Right.
Which one's bigger?
Bob.
Yeah.
So this is 3n plus 3 is bigger than 3n.
Right.
That means that if I was to expand each of these factorials, they're going to have a lot in common.
So,
Except for the last 3.
It's like, it's gonna have even more than that. It's gonna be like 3n plus 1,
Mhm.
3n plus 2,
Mhm.
3n plus 1. It's all gonna not be covered up by 3 sub n.
So I'll start by beginning to write down the denominator.
Okay.
The first factor, right, would be 3n plus 3. And like you said, I think you said it in the opposite order. I'm just saying it in this order. The one that's the next largest one would be
3n plus 2.
Do you mean the next smaller one? Yeah.
well, yeah. The of all the ones that are smaller, the largest.
Yeah.
Yeah, but yeah, and notice that there's nothing in the numerator for this to cancel with.
Right.
There's nothing in the numerator for this to cancel with either. And there's nothing in the numerator for that to cancel with. But I'm not done yet. If I keep going, the next term would be, the next factor I should say,
3n.
is 3n. And that does have something to cancel with, right? It's the first factor here, and the next one after that will cancel with the next one there. So we've done this a couple of times, so I'm just gonna kind of just say it in words and just write that.
Okay.
I canceled.
But it's called, no, that's not telescoping.
Yeah. Yeah.
If it was all but the first and last one, it would be telescoping.
Yeah. And then the last one, of course, this is probably the easiest of the 3, I would say. You got one more x on the top than you do on the bottom. So it simplifies to be x. Oh, hold on. I said everything's positive, didn't I? It's conceivable that x might not be positive.
So x.
These expressions will never be negative. However, this could be negative, and so this absolute value, I can't just drop it altogether.
It just applies to the next one.
Yeah.
Okay.
And that's important. And I'm going to go ahead and apply this same logic that I used right here to here.
Because that's an n plus 1.
Mm-hmm.
Well, are you going to expand that then?
In my head.
Okay. Like,
Yeah, I can see that the top is bigger than the bottom. In fact, it's going to be n plus 1. The next term would be n, and then n minus 1. But that second factor, the n,
Cancels out.
it's going to cancel with the first factor here. And the third factor, n minus 1, is going to cancel with the second factor on the bottom.
I'm sorry. I wasn't paying attention.
Yeah. I'm simplifying what's inside the parentheses. I'm not even dealing with the 3 yet.
Okay. So you said that's n plus 1.
Mm-hmm. Yeah. So
Okay,
the first
so-
factor is n plus 1.
Right.
The second factor is
N. Okay.
which happens to be the first factor in the denominator. Right. Cancel process. Yeah. So actually, that's all it is, isn't it?
Yes.
It's just n plus 1 cubed times this fraction. So as n gets huge, you're left with, I'll write it like this, I guess, n plus 1 times n plus 1 times n plus 1 all over 3n plus 3, 3n plus 2, and 3n plus 1 times the absolute value of x. Now as n gets huge, this part's not going to change. But this part is going to get closer and closer to what?
So either, I'm just thinking in the terms of the
Mhm.
highest degree.
Mm-hmm.
So can you say 1/27th?
Yeah. Yeah. This is going to be the numerator is going to be a third degree polynomial, and it would be a bit of work to actually see what that polynomial looks like. But all I need to know is that the first term is just n cubed with a 1 in front. The rest of the terms are going to be, will have no bearing on the limit. On the bottom, if you were to expand it out, it would be even more complicated, but this much I do know, is that the first term is going to be 27n cubed, and then a bunch of other terms of lesser degree. And so that being the case, as n gets huge, the ratio of the leading coefficients would be 1 over 27. So this would equal so it really depends on what x is. Depending on what x is, this limit could be bigger than 1, less than 1, or perhaps equal to 1. But we know it converges only if this limit is less than 1. So we only want to deal with the x's that would make this limit less than 1. Right? And at this point, I can see that those would be the values of x for which. Yeah. So now I can see that this is the interval of convergence is going to be centered at 0 with a radius of 27. So there's lots of different ways this question could be asked. It could be like, what's the radius of convergence? In that case, you'd say
27.
If they say, what's the interval of convergence? You're going to say
27 times 2.
Yeah. Negative 27. It's not the length of the interval.
Okay. What is the actual interval?
But the actual interval. What is the interval of convergence?
So then we plug in 27 to see if it's
Mhm.
equal to.
Yeah. And if this was like a 10-point question on the exam, if you got here, that's pretty good. You'd probably get 19 out of 20. Because there is two lingering questions that remain. It's clear that it diverges out here, and it's clear that it diverges out there.
But what at 27?
Yeah, like if x was equal to 27, then the ratio test would give you exactly 1. And in that case, it's inconclusive. So there's 2 remaining questions. To get full credit, you have to answer 2 more questions. And that is, what happens when x equals 27, and what happens when x equals negative 27? Right. So I would probably come back to so if x equals 27, right? Then this power series becomes a chapter 5 question. It becomes just a normal series. No x is involved, right?
Okay, yeah, yeah.
So does that converge or not? And likewise, we want to ask this question as well. I'm kind of doing one of the steps in my head. I should have written negative 27 to the nth power. But I went ahead and separated it to 2 parts, and that just makes it clear that this is an alternating series. That one's not an alternating series. Yeah. So, do these converge or not? Notice I can't use the integral test here.
Just not, wait. Is
with
that
the-
not decreasing?
Because with an integral test, you'd want to turn this into like a continuous function, right?
Yeah. Oh, but it can't be, yeah, that's
So the
right.
factorial is not defined for fractions,
Yeah.
right? So I just want to make that observation. It helps you to kind of whittle down like which test to use and which ones not to use.
That's a good, yeah.
Yeah.
So
You don't want to spend 10 minutes trying to use integral test and
And
then
then
realize,
you're like-
oh, wait a second, this doesn't even work.
Yeah.
You can't use integral test here. I'm going to guess probably the easier of the two is going to be this one, simply because it's an alternating series. Since it's alternating, it's enough, it would be enough to just show that this sequence would go to 0 if it does go to 0. If it doesn't, then that would actually answer this one too. Because then by the divergence test, it would not converge. Anyway, I'm just relying on my wits now. I'm not sure. What's the best way to handle this? In comparison, this is going to, these limits exist. The ratio test obviously won't help us because we know we're going to get 1. And the root tests, I don't think I want to go there. What else is there? Yeah, let's see here. This is a good time to review that. We had like a table, didn't we? There it is. Just to kind of review what we know. Where did it go? There it is. I guess divergence test is a good place to begin. So question, does this sequence, just forget it's a series, does the sequence go to 0?
Yes.
No. Because of the 27 n, no. Or 27 raised to n, no.
Maybe, I don't know. I honestly don't know. I
Well,
mean,
I think
that's increasing pretty fast, but this is also increasing pretty fast too.
Yeah, that n factorial cubed is raising pretty fast.
Mm-hmm.
So that I would say no because that then times the 27n.
Mm-hmm. So in other words, so that my sequence is a sub n is n factorial cubed 3n factorial times 27 to the n. Does this go to 0? Question mark.
So if you have 5,
Mm-hmm.
and you said 5 is 120,
Yeah.
5 factorial is 120, 120 cubed times 27 to the freaking 5th, all over 15 factorial.
Yeah, 15 factorial is pretty big too, though.
120. Well, you know, that's when we got calculators.
This is going to go to 0.
Let's go 15 factorial.
Hey, while he's punching these in.
Yeah, that's pretty. That's pretty huge. That's hundreds, thousands, billions, trillions. Yeah, it's 1.3 trillion. Let's just 3 trillion, and then 120.
What number are you plugging in?
5.
5. N equals 5. Yeah.
Hopefully that's close enough to infinity.
Yeah.
Times
What's 5 cubed?
27.
Is that 625? What's 5 cubed?
Yeah, no, it's going towards 0.
Is it?
Yeah, because it's 33,000. 5. Oh no.
Times 27 to the
5
fifth?
cubed. 5 cubed.
No, it's
But I
not
feel
5
like-
cubed,
but I
it's
feel
5
like-
factorial cubed.
You know, like
Five.
in my experience, when with factorials as compared to exponential functions, for relatively small n, exponents are going to increase faster.
Yeah.
Yeah, I mean, factorials they need a little time to really like do their thing.
But I'm saying, so this is 46 million is what 5 factorial cubed.
Times
yeah.
27 to the
Damn.
5th. 27 to the 5th, that's big. Yeah.
27 to the.
Oh, Professor, just one more time. So what was it? Polynomials is
Exponential. Okay. Yeah, no, I might have been lying. Times 5 factorial. Nope.
5 factorial is 120.
120 cubed. Yeah, no. 1, 2, so that's hundreds, thousands, millions, trillions, billions.
And did you multiply it by the 27 to the 5th?
Yeah, I did.
Okay.
27 to the 5th is like 14 million. Okay, well, let's try 10.
Wait, so what did you get for the top and the bottom at least?
42 trillion over 1.3 trillion.
So 42 trillion over what?
1.3 trillion.
1.3 trillion. So when A equals 2, at the 5th step along the way, it's still bigger than 1.
Oh, yeah, there's no way.
There's no.
Yeah.
100.
It doesn't take long before your calculator
Yeah.
won't be able to handle it, you know?
It's putting it in E notation.
So you really have to,
1.7.
you really have to rely on, some like mathematics to really go beyond the calculator
Conceptual
now.
understanding.
Yeah. Yeah, let's see here. I'm still kind of puzzling over this. It's
Yeah,
not-
what test could you use though? You couldn't like.
Yeah, the limit. Yeah, I mean, limits, as n goes to infinity, in 151, what do we got to go with? If I can show, okay, there is a theorem that's not on this table. If I can show that it's decreasing, and that it's notice that all these terms are positive.
Right.
So if I can show that there's a point beyond which that this is decreasing, that would prove that the limit would have to be. Now, that just proves the limit exists. I still don't know whether it's a 0 or not.
Yeah.
That's
So here's the
what I
question.
need.
I might have covered this and it probably blew past my head back in last term.
Yeah.
But there's no
Mm-hmm.
integral for a factorial, right?
Well, there is, but we're not dealing with it in this class. There is an attempt to,
Okay, that's-
although, but technically the factorial,
Mhm.
you can't plug in fractions.
Right.
But mathematicians have attempted to come up with a continuous function for which you can plug in fractions, but for which when you plug in integers, you get the same thing as a factorial. You know what I mean? And it turns out it's even differentiable, right? And I believe they call it the gamma function, right? But we're not going to deal with that,
Yeah, no.
happily. Yeah, I'm not really sure what to compare it with. What is that even?
Can we just plug it in
comparable to?
Desmos since it's a sequence?
I guess, just see what Desmos does with it. Yeah, let's try it.
This come back later.
Yeah. Yeah, I'm curious to see what it says.
Some.
So we got the sum from n equals 1 to, let's just be gentle to begin with, to 10, let's say. See if we can handle that. So that's going to be a fraction, that's going to be n, okay, n factorial raised to the third power, right, divided by 3n, in parentheses, that's, parentheses are needed here, factorial,
All right.
times 27 raised to the
Undefined.
n. Wow. So it managed to compute it up to 10. And it's 207. But because this exponent, the base of this exponent is pretty big, it might take a while for that factorial to take over. Let's just see if it can handle 100. Yeah, undefined. Not happy. 20. Okay, it can handle 20. How about 30?
It's
Oh.
a number, and the number is increasing.
Yeah, it seems like it's increasing, doesn't it?
It seems.
40.
Yeah. Make sure we stick
40.
with
But
that
I mean,
word.
it could be increasing and then eventually start decreasing.
Yeah.
It's possible.
But you can't just graph n factorial. That's what I was talking about. Like my idea was like, can we just get a graph of n factorial? Can
Oh.
Desmos do that?
Yeah.
Because I was gonna say graph
That's
n
true.
factorial.
And I am computing the sum here. And we're really asking a question about the sequence here.
Yeah, that's why I was saying like if we
That's
could
true.
graph n factorial and then graph 3n factorial and just compare them.
Yeah, let me just look at the
And run
sequence.
behavior, right? Where's the? Man, how do you do factorials on this?
You go to.
I don't have an exclamation point.
Yeah, you do. Go to functions. Go to stats.
All right.
Bottom left.
Tracking.
Oh, what the?
Oh, you see, you can't just.
Okay. Now I'm evaluating the sequence here.
Okay.
I left off the sum,
Okay.
so I can see that if you plug in so you already did it when n equals 5, right?
Right.
So the fraction ends up being about 18.96.
Which is 1.3 times.
Okay. And as I keep getting bigger, it looks like it's getting bigger. See how it's getting going like that? Does it ever start to come back down though? Bigger, bigger.
Nope.
It's 56 is okay. 57 is not okay.
We have no idea.
57 is still meaningful, but just not with the computational power of Desmos.
Yeah.
Right?
But it's possible that it does come back down further closer to 100.
It is possible. It is possible.
But it doesn't seem like it.
Doesn't seem like it so far. But yeah, I think
It's good.
but yeah, okay, if indeed, if it's true, if it is true that this does not go to 0,
Right.
then this does not converge.
Yeah.
And furthermore,
That doesn't.
Because
that
it's
doesn't
less.
converge either.
Yeah.
So maybe I would have given you 20. No, I would give you 19 out of 20. Because you got to at least mention. Yeah, you have to give me evidence that it had occurred to you.
That we thought of this.
Yeah, that you have to consider those. You know what I mean? And in this case, you might. I don't know. Even now, I'm not really sure whether that goes to 0 or not. But you could just say, I computed it up to 56, and it seems like it's getting bigger. So I'm gonna say if it gets bigger, then the interval of convergence literally is that. You know what I mean? And I think they'd give you 20 out of 20 for that. Yeah. I'll have to think about that. I'm not really sure what's going on with that sequence. It's not clear to me. And I am kind of restraining myself from using later stuff about power series. Stuff we're going to talk about
Yeah,
today.
don't do that because then we don't.
Yeah. Because
testing one day.
I have a feeling.
Yeah, if you don't give me 20 out of 20 on this, then I'm gonna ask you for the answer.
Yeah, that's fair.
Yeah.
That's fair. Okay. Yeah, so I think that's kind of tricky. That's kind of tricky. Yeah, so I don't know. If we get a lot of people watching my YouTube channel, then somewhere at the bottom there's gonna be some wise guys gonna be like,
Who knows?
it's obvious, man. Just do this.
You go to things, doctorate it.
Anyway, I'm gonna leave it at this for now. I think this is as far as I can push push through this one at this time. So,
Multiplying power series?
yeah,
6 point.
I'd like to find a power series for this one.
This is T3.
Power series for this one.
Is this 6.2 still?
Yeah, 6.2. Properties of power series. So it's a continuation. We saw some examples before of how to do arithmetic with power series. You can add them together, subtract a power series from a power series. And when you do that, you just kind of add or subtract the like terms.
Yeah, that was all that stuff we breaking down. None of the homework problems was like that though.
Oh yeah, okay. Well,
That's why.
Oh, okay.
I don't know if that's on the test. I need another refresher because, or at least none of the problem that we got to yesterday were like that. So.
Well, one thing that I do remember talking about is like we had two power series and I wanted to add them together, but one of them had an interval of convergence of like,
Yeah.
from like -1 to 1.
Oh, yeah.
The other one was going from -2 to 2.
Right.
And so when you put these two together, they're really only going to be valid where they overlap.
Right.
So, in a similar way,
I'm sorry, so the synopsis of that is do both convergence on each separately,
Yeah.
and then add the results, the
Yeah.
range of convergence together.
Mhm.
Okay.
Mhm.
Star.
Yeah. So, and you know, so far we only know one power series, but we've been discussing ways to kind of do a lot with what we know, right? We only know that if I take 1 plus x squared plus x cubed, keep going forever, it's going to end up being 1 over 1 minus x, provided that, not always, sometimes it equals that, sometimes it doesn't.
If it's a finite or infinite.
As if the absolute value of x is less than 1.
Oh yeah.
Yeah. And that's really important. You want to keep this connected with that. You need, the power series doesn't do you much good unless you know where it works.
Right.
Otherwise, you could commit this great crime of invoking a power series and then in some engineering application, and then use it for a number where it doesn't work and get bogus results.
Quotient, Sich,
Mm-hmm.
or those parabolic,
Hyperbolic
that's
functions. Yeah.
They can be sequences though too, right?
Yeah. I think we'll get there by the end of this chapter. You'll be able to come up with the series for those, the power series for those.
But not sine and cosine, right?
Yeah, we'll do those too.
Oh.
We do everything. Actually, we'll do it today.
We'll do everything.
Yeah. But yeah, I just want to go over a couple more properties of power series. 3 more actually. If I wanted to come up with a power series for 1 over 1 minus x squared, right? So the example I have in mind is a little bit of a silly example because I'm going to kind of do something simple in a hard way. You know what I mean? So, based on the examples that we've seen so far, I could come up with this answer very easily, right? By just taking this power series, the geometric power series, and just everywhere you see an x, replace it with
X squared.
yeah. So I can just take this series right here. And here. You don't want to leave this part out. That's part of it. When you do that, when you substitute here, make sure you substitute here as well.
Right.
And I can see that this is just the same as that, just with x squares everywhere. So the power series for this function, which is different from that one, is 1 plus x squared plus x to the fourth, x to the sixth, and so on and so forth. And that's only for those values of x that would make x squared plus 1. I left off the absolute value because the square is never negative anyway. But if I take the square root of both sides, I can sort of get a better idea of what that really means, where that is on the number line. And that is when the absolute value of x is less than 1. So coincidentally, it ends up being the same interval as it was before. Just a coincidence, though. So there you have it. Okay. But it is kind of curious to note that 1 over 1 minus x squared could be thought of as
1 minus x, 1 plus x.
yeah,
What? Oh, okay.
right?
You just said factor, you know what I'm saying? No, I have no idea what you're saying.
Right. Okay. There it is. So, and so in other words, I could think of it this way: find the power series of this and the power series of that, and just multiply them. See, it's kind of a different way to hopefully get the same thing.
So that 1 plus x is the same thing as 1 minus negative x, right?
Oh, right. Yeah, I guess so.
So when you substitute that into those x's, though, the odd ones are still going to be negative. So wouldn't it be an alternating one? Or so if you have to factor out the negative 1 to the n?
Yeah. So right here, this one's easy. It literally is the geometric series. This is a geometric series, except everywhere I see an x, I have to replace it with
Negative x.
yeah. Right. I guess I should be thinking about the interval of convergence. We said before that if you add two power series, then the interval of convergence would be the overlap of the two.
Section?
I think the same would be true when you're multiplying two power series. I ask because I don't know. Let's take a look. This is in your book.
But so if it's addition, well, you got to come up with 1 because we already know the answer is 1.
Well, you know that the answer is 1 plus x squared plus x to the fourth plus x to the fifth. That's the power series?
But the convergence is
oh yeah, the interval of convergence is 1.
is 1, and we know the first half is 1 also.
Right, yeah.
So if you the second one,
Second
because
one
it's
is smaller
x,
though, right?
but it's x squared. So
Mhm.
1 plus x plus 2x, because
What? What you saying?
so negative x plus x squared, or
Yeah, but that is negative x cubed. And that's a
yeah,
minus.
it's always going to be an x left over, so it's going to be 1 minus 1 plus x.
What do you mean?
So
Yeah. What did you say? I was
no, because it's addition. It's not multiplication. Yeah. Okay. Yeah. So as you're saying.
Yeah. Well, I just was consulting the book. It says here, if you have two power series that converge on a common interval I, then the product is going to converge on that same interval. So, yeah, it's just the same as when you're adding. It's the overlap of the two. In this case, it just happens to be that both of these, So yeah, maybe I should write that down actually. This part of the product converges when this inequality is satisfied. This one converges when this inequality is satisfied.
What's the absolute value of negative
The absolute value of negative x is the same thing as the absolute value of x. So they literally are the same interval. So the product will converge in the same place. So yeah, that's worth noting. But yeah, how do you multiply these two power series, right? It's kind of tricky. Well, I just erased the screen, but what the screen does is, what the book does is it gives you sort of a formula for the coefficients, okay? And yeah, I guess it would almost be a better example if I had actual numbers here. Notice that there's a 1, a 1, a 1 are the coefficients. Here, the coefficients are 1, negative 1, positive 1, negative 1, right? But whatever the case is, you would, sometimes when I'm multiplying two polynomials together, one way to represent that is with a table. Usually my table would be a nice box, but this one that keeps going forever. I have things like 1, x squared, x cubed, and it just keeps on going. Each of these with a coefficient of 1. The second factor of this product is going to be the first row will be 1. Everything here is just going to be multiplied by 1. Everything along here is going to be multiplied by negative x, positive x squared, negative x cubed, and so on and so forth, right? And what you get is a whole bunch of rows and a whole bunch of columns. And I'm hoping that if I just look at this much of the table, it'll be clear what's happening on the rest of the table, right? So let's do some basic pre-calculus. 1 times 1 is 1. 1 times x is x. 1 times x squared is x squared. And x cubed. And it's pretty clear to me, although I didn't write it down, how this is going to continue. Negative x times 1 would be negative x. Negative x times x would be negative x squared, negative x cubed, negative x to the 4th. And it's clear to me how the pattern will continue. Likewise, x squared, x cubed, x to the 4th, x to the 5th, negative x cubed, negative x to the 4th, negative x to the 5th, negative x to the 6th. The pattern continues in an obvious way. You can even see, if you look at each column, it becomes clear like what's happening in each column as well. Each column is an alternating sequence, right? They're all ascending in a pretty predictable way. It might be a little more complicated if I had like more fractions and various coefficients for these. And most of the time, the coefficients are fractions if it's convergent. Anyway, so as a power series, what I'm trying to find is this. What do I put here? What's the constant term? What's the coefficient for x? What's the coefficient for x squared? What's the coefficient for x cubed? And so on and so forth, right? And what I can see from here is that those coefficients are going to come from the product of these two power series. And the way I compute those power series is I'd have to really do a lot of multiplication. But after you multiply, you can see how before you're done, you have to combine like terms, right? So like for instance, there's only one constant term. And although there's a lot of entries in this table, more than I've written, only 2 of them are linear terms. See that?
I'm sorry.
Of all the entries in the table, including the ones that I haven't shown, only 2 of them are linear terms.
Okay, yeah.
Exactly 3 of them are quadratic terms.
Yeah.
Exactly
4.
4 of them are cubic terms. And although I didn't show them all, you can see that there's exactly 1, 2, 3, 4, 5 fourth degree terms. And so really if you're going to come up with power series, you're really interested in the diagonal. Well, the formula you see in the book is a formula for how to compute the diagonals, basically, symbolically at least. But it's a little, I feel like it's a little more enlightening just to kind of visualize it as a table. So yeah, so I can now see, if I look at that table, I can see that the constant term must be
1.
yeah. The coefficient for the linear term must be
1 or no? What do you say? If there's 2, one's negative.
well, because one's positive and one's negative.
Are you saying multiply them together?
No, add them.
Oh.
Because after you multiply these out,
Yeah.
you're going to start combining like terms,
0.
right?
Yeah. Okay.
These are the like terms, right?
0.
Yeah, so those are going to add up to 0, right? But the important thing to take away from this isn't that it added up to 0, it's that it was this coefficient plus that coefficient.
Right.
The way you would find, or without the table, you would be taking this coefficient times this coefficient
Yeah.
plus this coefficient times that coefficient,
Right.
right? And the coefficient for the quadratic term is going to be,
X squared.
yeah, these are going to cancel, leaving you with just 1 x squared. But the big takeaway from this is this. This is exactly what the formula book is telling you. Is that, where did that 1 come from? It came from taking this product, 1 times 1, plus this product, 1 times negative 1, plus this product, 1 times 1. You see that? See, you're getting a quadratic term from here. 1 times x squared is x squared.
Right.
You're getting a quadratic term from here. That's x times negative x. That's negative x squared. And you're getting a quadratic term from here.
Oh,
1 times x squared.
Tracking.
See what I mean? That's what, so if you want to list, if you want to bypass the table, this is your thinking. I'm trying to find the coefficient for the x cubed term. Well, it's going to be 1 times negative x cubed. That's an x cubed term.
Okay.
It's x times x squared. That's positive x cubed. It's x squared times negative x. That's negative x cubed. And it's x cubed times positive 1. That's positive x cubed.
0.
Yeah. So, so you really have to consider, when I'm looking at the diagonal, I'm just looking at kind of like, I'm kind of going from left to right and right to left
Yeah.
in each part.
Seems easier with that table.
Yeah.
Yes.
So 0.
Unless on the test, we're working not at the numbers start at 1,
Mm-hmm.
and then like 30 and stuff.
So yeah, you got to go far enough to kind of see the pattern, and in this case, the pattern is relatively simple, I think.
1 0 1 0 1 0 1 0.
Yeah. When can we assume that this is a pattern? Like this is the pattern.
In this class, it's good enough to just do a bunch of them and say, I'm pretty sure.
All right. Cool.
Yeah. To go beyond that, you'd have to produce a proof.
Yeah.
Some sort of a justification. And I'm not really holding you to that for now.
For now.
Yeah. So yeah, and notice it agrees. I didn't show the linear term, but you can think of this as being 1 plus 0x
Yeah.
plus 1x
True.
squared plus 0x cubed
Yeah. Okay.
Yeah.
plus 1x to the 4th. So we get the same thing. So I think this is the worst case scenario, is multiplying
Oh, okay. I was going to say
2
this
power
example.
series. Yeah, multiplying 2 power series can get pretty hairy.
Is that on the test?
I don't know. It is not, but I suppose
Could be on the next
it could be on the final. Who knows?
Additions.
Right. Anyway, so there's that. A couple more examples I wanted to look at real quickly. I think that's, again, that's the worst case scenario. The next two I have in mind are easier than that, at least.
Than that.
Yeah. So for example,
You can't listen, Professor. It's
You can't.
easy. Yeah.
it's all relative.
To us mathematicians, the next one is easy.
So notice, actually, I think this actually, I dare say, fun.
That's gonna be rough, man.
So we all know that if f of x is 1 over 1 minus x, a question that I could have asked back in differential calculus is what's the derivative? How do you do that?
Yeah.
Yeah, you could do that. Or you could just think of it as power rule.
Yeah.
Either way, you get the same answer.
Them freaking zeros.
But I do need to use a chain rule here. Derivative of the inside, that's -1. So negative negative makes a positive, so that's equal to this. That's a question that could have been asked in differential calculus. And I'm confident that if I ask you that question, you can come up with the same thing. Maybe with a quotient rule or otherwise, but you'll get there. But what I want to do now is, what's the power series of that?
Well, no, not the square.
Not like that.
Yeah.
See, the power, if we were to do this the way I just showed you, this is like, with the technique I just showed you is something that you do when you just can't do anything else. It's like, okay, I guess I gotta. You know what I mean? But in this case, I would be taking like more like this.
Right, okay.
That one was a 1 plus x, right? So the terms are going to come out differently, actually.
Yeah.
Actually, you know what?
Wouldn't they be the same?
It won't, because there'll be no negatives.
Maybe x plus
Well, yeah.
x squared plus 2x.
I wasn't planning on this, but I think I'm realizing this actually isn't so bad. If you're to make this table, it's pretty much the same table except there's no negatives.
Yeah.
That means that there's going to be one constant term, and it's 1. There's going to be 2 linear terms. It's going to be a 1x and 1x.
2, 3, 4, 5, 6. Dot, dot, dot.
Dot, dot, dot.
Well, that wasn't so bad.
Yeah.
The interval of convergence for each of these is the same. So the interval of convergence for this one must also be the same. Oh, okay, okay.
Okay, I'm sorry.
Mm-hmm.
So when we find the interval of convergence, we were saying that a to the n times x to the n, if x is between -1 and 1, that multiplied with a to the n will be converged, will converge at a number.
Mm-hmm.
Okay. That formula 1 over 1 minus x.
Mm-hmm.
That is the. Help me out here.
What? 1 minus x?
Yeah, 1 minus x squared. 1 minus x.
Mm-hmm.
That's the sum for the the geometric series. Find where it converges, and then what are you trying to say?
So that gives me the sum of the
Series.
series.
Mm-hmm.
Yeah, but if you multiply it with another,
Oh, no. I'm still trying to make sure I know where to plug and play. So given a to the n,
Mhm.
I need to find 1 over 1 minus x. I need to find the sum equation.
Yeah, yeah. We're trying to find the power series.
Right.
Yeah. Mm-hmm. So when I say we're trying to find the power series, it's given that we have these powers of x,
Right.
but it's not clear what the coefficients should be, or even if such coefficients even exist.
Are you done?
I mean, if you're gonna add on to it.
Well, my question is, but why would we do that? Why would we even multiply it if you told us that adding them, which is like easier to me, is going to be the same interval of convergence?
Well, I mean, yeah, I mean the power series for this and the power series for this, both of those are meaningful, but those are different power series because these are different functions. Like this right here is literally just that function.
Yes.
And that's different from this one. These are different functions, so they're going to have different power series. So sometimes you got to multiply, sometimes you got to add.
Okay.
You know, but they aren't the same thing.
Yes.
Anyway, like, okay, so this was, we could use that, you know, that multiplication technique I showed you, but we didn't have to. In fact, since this function is merely the derivative of this function, you can think of it as just taking the derivative of both sides, right? What the theory tells us is that if it converges
Oh yeah.
absolutely, right?
Yeah. Alright, yeah.
If I differentiate both sides,
Same, take the derivative of x plus x squared plus x cubed is the same thing right
Yeah.
there.
Yeah.
Interesting.
So does that work every time?
So the 1 becomes a 0, the x becomes a 1, x squared becomes 2x, x cubed becomes 3x squared,
It's
and
crazy.
this
Dog.
becomes,
I wouldn't have noticed that until you had said it. You know, I'm looking at the book.
yeah,
So that works on all of them.
yeah, and that's, I'd say this is easier than doing that,
Yeah.
right?
Yeah.
So you can differentiate, you know? I mean, we all knew we could differentiate polynomials, but it's quite a different thing where, when you're going out to infinity, you
Yeah.
know? And we're only looking at scenarios where you can do that. There are power series for which you can't differentiate. And so, but we're gonna, and
Power series that aren't continuous.
yeah, it's gonna be like, basically, you know, that's why we need to talk about absolute convergence. If a function converges absolutely, actually, if you have a sequence of functions, and that's what this is, a power series is really a sequence of functions that are being added up, then you can differentiate term by term all the way out to infinity if it converges absolutely, or the term they use in that context is uniform convergence. You know, we're not going to go that deep. So for the things we're dealing with, you can differentiate. You can even integrate. You might recall
Yeah, natural log of absolute value of
Mhm.
1 minus x.
Gotta be careful though, because the chain rule does play a role. You know, because that minus right there.
Okay, yeah.
If u equals 1 minus x, the derivative is going to have a negative could pop out. So I think this is going to end up being the natural log of the absolute value of 1 minus x plus, oh yeah, with a minus in front,
Negative in front, yeah.
plus c.
C.
Yeah.
Roger.
Yep. So yeah, let's see what happens if you integrate both sides here, right? If you
X 1/2 x squared.
mhm. Yeah, antiderivative of, now this c, I'm gonna actually, you know, these two functions, each of those is gonna have an arbitrary constant, right?
Okay, yeah.
I'm gonna choose to put it on the left hand side. All right. So in fact, I'll write it right here.
In the front, yeah.
Yeah. C plus
X
x.
1/2 x squared. So on that one, we're integrating each of those terms. So 3/2 x cubed.
1/3, I think.
Oh yeah. Yeah. X to the 4.
And that should simplify it down to negative natural log of 1 minus x.
What? How? Mr. Abel, give me a break, please. That doesn't seem like that goes to that.
What's that?
That doesn't seem like it is the same thing. When you're
That's
saying
true.
it simplifies that. That doesn't seem like.
Well, let me do one more thing, and then we can investigate if that's agrees with reality. So I'll wrap this up real quick. Yeah, so notice that I'd like to know what C is. And in this case, I do know what C is, because if x equals 0, that tells me what C is, right? Because if x equals 0,
all
then
zeros and natural log of 1.
natural log of 1 is 0.
Negative natural log. Yeah.
All these would be zeros. The only thing that's left is this. And so I can see then that C plus 0, I'll write like this.
So basically, basically though, we'll have to solve for C.
Yeah.
It might not always be this easy.
It's always going to come from just plugging in a number. In
Right,
fact,
right.
you're always going to plug in the center of the interval of convergence.
Always plug in the center.
Yeah, because
Okay.
it's going to turn these into zeros.
Right.
If it was anything other than that, it won't be as obvious.
Right.
Right. So I can now say that negative natural log of this is equal to x plus 1/2. Actually, with that minus x plus 1/2. X squared plus 1/3 x cubed, etc. And again, since when you integrate term by term, it's going to have the same interval of convergence. So